So last time we talked about abstract tasks, and we defined what abstract tasks are. And we talked about like the representation of the belief in far transfer in different forms, like in general education, we talked about like math in high school and university, about educational testing like standardized tests like GRE, SAT, and intelligence tests as all examples or different representations of the belief in far transfer. And the reason was that most of them somehow had this idea of abstract tasks and abstract education that was not intended to be applied to the real world problem directly, but they had some form of belief that if you practice these, you will need them or they will develop you in some way or other for the future task or future real world task. So today we're going to talk about the specific instances of low fidelity simulators. So we talked about practicing abstract tasks, and which was inherent in the belief in far transfer. And those abstract tasks are those that do not on the surface look like their real world, anything real world, like real world systems or tools or anything of that. And the reason to use low fidelity simulator, or some main reasons of doing that, is basically it's because the kind of skills that the person acquires by practicing with low fidelity simulators are not specific to any system or any specific system or tool, but is generalizable to many systems. And at the same time, when you have this notion, then you can just train certain skills or with one abstract task, and that can be generalized or applied to many specific systems. And this increases the speed of training. And of course, reduces the cost, both because it's just one training for all and because it uses very cheap, low fidelity simulators. And so the goal of using low fidelity simulators is basically these reasons, and those who want to design low fidelity simulators should look for the shared aspects or shared characteristics of different tasks and derive that or represent that in some way and like shape it in the form of a training material or training task. The key question in doing that, like imagine yourself to be someone who wants to produce or design those low fidelity training materials. The key question for you is, can we design one single task that is represented or shared between certain real world tasks? So if you have like a category of tasks like troubleshooting or certain different types of surgery, can you find a shared aspect or shared behavioral characteristics or anything of that kind between all of those specific tasks in the same group? That's the question that any person who wants to develop abstract materials, low fidelity simulators, should ask at first. So the question that I have from you is, if you were writing something from here, so it's basically, most of it is what we talked about last time, but it's just this question of whether we can find these shared characteristics or not. So the question that I have from you is that how can we do that? Like if we have certain tasks, imagine you have certain specific tasks in the world, how can you find their shared aspects? Like, should we be looking for like completely different tasks, or should they be in the same group or same vicinity of certain types of tasks? And if they are, what should we be looking for? And what should we do? Yes?
My name is William. Imagine you want to start with tasks that are similar and then kind of work out as the same kind of doing the same thing.
So how do you define like tasks that are kind of similar? Like,
Just the same skill set, I guess. Like using math or something, or if you're, you know, if you have like time duration, you'll solve the issue.
yeah, so you start by thinking about like a group of tasks and then finding what is shared between them. Othman?
You also look at if they have the same goal, you might go to the same, have a simple shared task.
So finding if those tasks have like relevant or same goals, and then approaching to see if there is anything shared between them. And in answering the question of what is shared between them, what do we exactly mean? Like, what should we be looking for? Like, is it, yes? Yeah. So like, do you have the experience of working with different programming languages and then finding, like, what did you find as shared things between them?
So I know it's like called assignment or value. It's like it's just different syntax.
Okay. And you were Stanley, right? Okay. So yeah, if you think about a task like programming as like general task of computer programming, then some general structure comes to your mind, like defining variables. Like most programming languages, except some extreme ones, most of them have this defining a variable, variable type, defining loops, conditions, if then, functions, blocks of code, calling the functions, and those types of things. These are mostly shared between most mainstream programming languages like Java, C++, C#. Most of like this mainstream programming languages have these properties. So if you can find, or if you can just train or teach these aspects, or better to use the word train because they have to practice. If you can just do this, then that person or that trainee can have like a general idea of what programming is, and then can focus on a specific programming language, learn its specific syntax, and working with a certain IDE or software to develop the program. Yes?
My name is Alex. I believe earlier in the semester we talked about tasks and subtasks. I believe that would be applicable to comparing tasks for shared things. You would want to compare the subtasks on abstract.
Yeah. So basically, if I want to rephrase, you should do task analysis at first. Like find the smallest unit of human behavior and then seeing, for example, between these two tasks, what are shared between them. And when you find those shared aspects, designing a simulator or any training material that can train those shared aspects. Yes, all of these are good answers. Any other?
I think, Shivansh, I think apart from previous clause, the tools are being connected with us, so that the tool we apply and it's here there. And in this, that's one thing which has access to those tools.
Yes, if you do not have that much knowledge about certain tasks, one thing you can do is just to go in field and then see what are the tools that different tasks use. And if there is a certain level of tools that are shared between certain tasks, then you can make them as candidate tasks that have something shared and then go deeper finding those shared aspects. But basically, if you think about it this way, there are certain tasks that need using certain tools. And if you just train using those tools, then that person is able to use those tools for specific jobs or tasks that that person is responsible to. Yes, any other? Yeah, I would say those were all good ideas. Here we want to like give a specific example of how to find like a shared task that is like abstract task that is shared between several specific tasks. And it is troubleshooting. And we just talked about this and we saw these examples of troubleshooting mechanical systems and electronic systems. There are two different types of systems. And we said that mechanical systems usually have like certain components, connections, but their behaviors and properties are slightly different because they work with fluids, with materials more than electronic systems that are, again, components and connections, but it's basically electrical current that defines their direction and activation. So we have these two different types of systems, but you can find similarities between them. And those similarities are, as I said, all of these systems have certain components. And by component, you can think about like in mechanical system, like you can think about the engine of the car as one component, which can be divided into subcomponents, like radiator, like you can go deeper, transmission as one holistic component. Again, you can break it down to smaller components. And in electronic systems, things like capacitor, like ICs, like these things that can be considered as components. And in all of these systems, both electronic and mechanical, these components have connections, some way of connection. So not all components are always connected to all other components, but there is certain pattern of connections between components. And in troubleshooting tasks, we see the output of the system, which is not supposedly, which is not working properly. And so there is a fault. So when we see the fault in the output, we trace it back to the components by trying different components or trying connections. So if you think about like definition of system in like high school definition, system is anything that has input like an internal unit or processing unit and an output. And here is exactly the same. So we have input, we assume the input to be active, and the output should also be active in some way. And if it's not active, there's something wrong with the processing unit or internal part of that system. So do you have any question about this holistic picture? We will talk about more like specific examples of what we mean. So these may look a bit like abstract and a little incomprehensible, but we'll go into more detail. So this is just like an abstract troubleshooting task. And to talk about like a specific example, is a research by human factors researcher, psychologist named William Roos. And it's early in 80s. And in that time, especially in the military, they had the concern of training their personnel of certain troubleshooting skills that could be applied to a lot of different types of systems, just like what we talked about as the goal of using low fidelity systems. So they wanted to create a low fidelity model for the task of training troubleshooting. Again, just as I said, imagine a system that has input, internal units, or processing unit and output. And this itself is something that is shared between both mechanical, electronic, and almost any system. When we talk about a system, this is one property of that system. And we assume that all of these inputs as we define to the system are active. So all outputs should be active too. Now you might say, why should all outputs be active? They might, I mean, in binary systems, if all outputs are active, it's always one, and it doesn't mean much. But for the sake of troubleshooting, we assume that all inputs are active, all outputs should be active too. This is just for the purpose of training. And so in this picture, if all outputs are not active, then there's something wrong with the system. So at least one component is faulty. So we have a system, there are inputs, they're all active, there are outputs, they should also be all active. If they're not, there's something wrong. And we should find that faulty component. And so our attention should be on the output. If they're not all active, then we should find the fault. So again, you should remember that whatever we are talking by now, they are shared between all troubleshooting tests. Mechanical, electrical, within each of those old systems that you can think of. And so Roos, as a researcher, proposed using the low fidelity training simulator for troubleshooting tests. And if you think about the system that he proposed, it's something like this. Like we have components as these like circle or whatever it is, circle-like shape. These circles are each nodes, and you can see the connections between these nodes. And these connections have a direction. And you can see that, for example, this is the input, this entire thing is a system, and this is the output of the system. So, and you see that the general direction of these connections are basically from left to the right. And so this is kind of a replica of a circuit or mechanical system that has components and connections and nothing else. So The assumption here is that there's only, I mean, in this specific task and this research, there's only one faulty component. Just to make it very simple to people who have zero experience in troubleshooting tasks, there's only one faulty component. Another assumption is that each component can have multiple inputs and outputs. So as you saw here, each component can have 1, 2, 3, 4 input and output. And if the component is working properly, imagine that we have a component. If all the inputs to that component are 1, that component produces 1. It's kind of, if you're familiar with electronics, basic electronics, it works like an AND gate. So if one of the inputs are 0, then it produces a 0, regardless of other inputs to that node. I'm just giving this as an example. You do not have to like memorize the entire way that this works, but this is just an example of how this experiment or this example works. So again, for each node, if it's not faulty, all inputs are 1, it produces a 1 or ones in the output. Otherwise, if the component is faulty, or if there is a 0 to the input, it produces a 0 or zeros in the output. And so the trainee sees the output. There is 1 or multiple zeros in the output, which means there's something wrong with one component in the system. The assumption was that it's only one component that's causing the problems. And the goal is to find that one faulty component. And at each step, so the trainee or the operator can, at each step, try the connection between two components. So is this connection 1 or 0? Again, next time, is this connection 1 or 0? Until he finds the faulty component. And so if you think about it this way, the best performance would be to find the faulty component with the least number of trials or least number of tests. So you test n number of connections. Your performance would be better if you find the faulty component with the least number of tests. So again, if we go back to this model, then you see that, for example, this is like an example of how a trainee found the faulty component successfully. At first, this connection is tested, 22 and 30, just out of random. And you see that these are zeros, and 22 to 30, this connection is tested, this line. And it says the result is 1, so it's working. Another one, 23 to 30, this one. So the previous one was this one is this. The question is this active or not? And again, this is active because it's 1. Next time, 30 to 38. 30 to 38, this one. So this was tested, this was tested. These are all both 1. And now that trainee is trying to figure out whether this one is faulty component or not. So the next move is 30 to 38, this, which is also 1. 31 to 38, this. So this was tested, this was tested. So as you can see, it's kind of going in order to find like one section to see if it's working or not. 31 to 38 is 0. So there's something wrong. We should just diagnose this and go back. This one is 0, 31 to 38. The next move is 24 to 31. 24 to 31. This is 1, 25 to 31. This is also 1. And of course, because these, we said that 23 to 31 was already tested. Sorry, 23 to 30 was tested. So if it's producing 1, it's producing 1 for all outputs. And the same goes for 22. So this is giving 1, this is giving 1. 24 to 31, again 1. 25 to 31, again 1. There's only one possibility, that 31 is not working. So 31 is the component that is causing all of these problems. I know it was a bit boring going through all of these, but that's the kind of steps, logical steps that you would take to find the faulty component. These are outputs. Yeah, these are the outputs. They should all be 1. If there are zeros, then it means that there is a faulty component, at least one faulty component. So the fewer steps, like here, there are 6 steps. 1, 2, 3, 4, 5, 6. 6 steps that the operator it took to find the faulty component. If you can find it in fewer steps, you do a better job. And the more steps you take, your performance is not as good. And the goal is to find the faulty component in the least amount of time with lowest number of steps. Yes.
That would mean any one of those would be
44. This one.
so that means every single sort of result that could be.
So yes, but 44 itself might also be faulty because it's producing 0. So if there is a faulty component, all inputs are 1, that is a faulty component, it produces 0. Yes?
Oh, I'm sorry.
You go ahead.
Can you explain how 32 isn't the faulty component?
Why 32 is not a faulty component?
Or if we want to talk about after class?
Yeah, we can talk about after class because I didn't go through like whether there's other possibilities or there is like a mistake or anything in the system. But I just went through this and saw it's working at least for one component as that assumption was. Yes?
So if you test like, let's say test 44.
Uh-huh.
And you, although other nodes around it don't work, should you test the nodes around it as well?
So if it's 44 that is not working, then you can argue with high likelihood that the assumption of only one faulty component is not at least is not working here. There should be more faulty components because you see other zeros here. But this is just to give you a general idea of how this steps and how this activity works. And you can see that it's kind of a logical inference task that you see the output. So you logically infer that it should be this or that. And of course, it takes certain steps. And in this specific task, fewer steps are better, but in some other more sophisticated kind of task, for each step, there is like a cost associated with each step, which is trying to replicate the reality more accurately. So this was one example of probably the lowest level of fidelity then you can go in training a troubleshooting task. That doesn't look like any real system with any detail. It's basically free from details. And it's just a bare bone of logical inference task that you can see in any troubleshooting task in the world. So if you think about this task or this material for training, what do you think are the benefits of using this in training troubleshooting? We mentioned them, but if you think about this specific case, what do you think? Yes, so it's basically the generalizability of the skills that you learn. And if you think about like practicing this logical inference, you get used to doing logical inference. And then at least that component of logical inference in real troubleshooting tasks, it makes it easier for you to do that. But if you do not have any practice, then this is added to anything that you do not know in the real world troubleshooting task, and it makes it a bit, at least it takes more time for you to learn. So this at least helps learning one aspect of the troubleshooting task, which is the logical inference.
And pretty much build off of what was said. Troubleshooting inherently is more or less like trial and error because you don't know what's wrong. So you have to kind of go through the process.
Mhm.
You got doing something like this, constantly have to do trial and error and trial and error.
Mhm.
Kind of build up this basic.
Yes, exactly. It's kind of like practicing with trial and error. And this itself is something that if you practice more, you get better, and you will have less error in developing this troubleshooting skills. Yes, any other benefits that you can think of?
Like it can be more time efficient. Somehow, like this is a, let's say, easier task to perform comparatively like hypothetical systems. Where essentially practicing the core concept of the task, and you don't have to deal with like holes or other.
Mhm. Yeah.
You can save the time and do more reps.
So yeah, basically it's more efficient to train tasks this way because you are not dealing with the details and specific tools. Sorry, what was your name again?
That's it.
How do you spell that?
SHIH.
Oh, okay. Yes, Victor.
One off, efficiency, I think, practicing with troubleshooting. They sort of they might find you might see things that they would have forward to. I think
Mhm.
previous experience from perspective of how to approach the situation.
So you think it's even useful for those who are experienced?
Yeah.
That gives them kind of a new perspective of the troubleshooting task so that it might influence their future performance. Yeah, that's a good idea. And I think it's also, there are research in doing that whether, because these systems are usually used for people with almost zero knowledge and experience in the task, but whether the question of whether it can also be useful for those with more experience is a good question. And there is a research on that. Yes.
And when we, like when you're practicing, you have more general sense. These systems are always evolving, and so if you're practicing it in more specific sense, it may not like translate so that you would use that system or like troubleshoot that system so that you don't back.
Mhm. Yes. Yes, it's a good point. Because if you get trained with specific systems, like say it was from early 80s, but this basic concept exists today or in the next decades. But if you practice in that time with specific systems, those systems might be not in use today. And so your knowledge of that specific system is no longer useful.
Well, since the low fidelity simulator is not pen and paper, it also gives the opportunity for people to do the test, like repetitively, do the test again and again, which can build the sort of problem solving skills that which can apply to many other departments.
Yes, exactly. It's kind of like solving a Sudoku puzzle or something like that on a piece of paper. And you can, this itself is like something because it's easy to develop, it's easy to distribute, it's easy to send this training materials to anywhere in the world. And this availability and portability is also something that, and also doing the task itself, you do not have to be like in certain setting, prepared, wearing certain things or using certain tools. You can just do it anytime, anywhere. Imagine the same thing exists in your cell phone. You can just do it anytime. And your name. Okay. So yeah, these are all benefits of practicing with this simulator. But if I want to just point to certain or important aspects of its benefit, it's fast to learn. So you basically spend like what, a few minutes of learning about its basic rules. It is easy to practice. Once you learn the rules, then with a bit of practice, you know what to do. But one might argue that to develop skills in doing that, you have to spend more and more time. But to learn the basic principles, you have to spend relatively short time to do that. And as I said, it's easy to distribute. You don't have to use like a computer simulation or certain systems or tools. And the same thing, it's basically something that can be printed on a piece of paper or with even like you can have it in your, like as an app or something in your cell phones or anywhere. And again, the lower you go in the level of fidelity or abstraction, the higher would be the level of generalizability of this skills. And the more you become specific, the less generalizable this skill would be. Now, of course, someone who practices with that level of like abstract material, it's not like readily applied to some specific system in the world. That person still needs to learn some basic working of that specific system, but this would be a much easier process for that person who is already trained with low fidelity materials. In the same, I mean, if you have any question about that low fidelity system, its benefits, or if you think there are certain problems, and if you do not have any comment or question, I would say that in the same line of research, the same researcher who's compared this low fidelity example that we saw with another model or another simulator that has a slightly higher level of fidelity. But this model is still considered as low fidelity. So to make it a little bit more like real world systems, the proposal was something like this, that you can see that there are, again, components and connections between those components. Here, components are two types of components, not just one type. And it is these rectangles, and another one is this kind of hexagon. So there are two types of components. And as you can see, the higher complexity is that the output of one component can be the input of another component in the same level, or sometimes it can even go back, or it can like go straight from one component in this level to this level. So you can see that the complexity of the connections is higher here. And there are two types of components, each having different rules for its input and output. But you can see that the output is still here, like 1, 0, 1, 0, 0. And we also assume that inputs are all 1. So the assumptions for this one, in addition to the rules for the previous model, there are two types of components, as I said. The rectangles work like AND gates. So if all inputs are 1, all inputs should be 1 for the output to be 1 for each component. But those hexagons is not like that. It's like OR gate. If there's at least 1, it produces 1. So the only way that it produces a 0 is that all inputs should be 0. So it's the other way around. For AND gate, all inputs should be 1 to produce 1. If there is 1, 0, it doesn't produce a 1 for the output. For the OR gate, the only way that it produces a 0 is that there should be all 0 in the input. And if there is at least 1 0 in the input for the OR gate, the output will be 1. You don't have to learn these details. And as I said, another difference is that the output of each node can go back as the input of other nodes in the same level or previous level. And also, just like the previous one, here the performance criteria is that fewer steps in finding a faulty component is better performance. So in the same way, I don't go through the details, but just these are the tests of certain connections, 20 to 25, which is this, is 1. 13 to 24, this to this, which there is 1 direct connection between them. It is 0, 15 to 13, which is this to this, which is this. Also 0, 8 to 15, 0. So you can see that it's tracing back 8 to 15. This 0, 1 to 25. So it all goes back to 1. 1 to 25, there is one straight connection from 1 to 25, which is, I think, this one. And by these, again, by logical inference, it found the faulty component, which is this 1. So this is another example. Just like previous one, we didn't go through the detail, but we assume these steps to be correct and the faulty component to be 1. So it took 5 steps for this example to find the faulty component. And if you think about this a little bit more sophisticated example, which basically corresponds more with the real world systems because there are different types of components, the connections are a bit more complicated, just like this more recent example. What are the benefits of this one compared to the previous one? Yes?
This one just a higher level of problem solving. I think this one will be better in conjunction with the first one, so you introduce them with the first one to get them thinking that way, and then you introduce this one to train them even more.
Yeah, I think that's exactly what they did. And they tried just having trainees with zero knowledge start with the second one, but it took them much longer time to get used to the second one compared to those who switched from the first one to the second one, who had an easier time doing the task. But yeah, that's right.
I think that just similar to the example that we had for the like when you start with the most basic version, when you move to a simulator that was moved, then you go to the real time. So
Mhm.
as you mentioned that this component, like this second part of the training had more real life elements. So it helps practice in the most basic one, then you do it in actual life. So you know to do it this sequence. It's a more streamlined process. than
Yes.
directly, you know.
Yes, it's kind of a direction towards like a real world system. And you have some people who develop these materials that would say, well, this is one step closer to the real world system. And again, one step, one step, one step. And then the more you get closer to the real world system, the more the materials would be specific. And in the end, you see that there's like a working knowledge of the system that you should have about that specific system. But as you do that, as you move along to more higher fidelity systems, you will also lose the benefits of using low fidelity system, unless if it's practiced like in this order. Any other thought on the benefits of this one? So basically, because it is still low fidelity, it is still a generalizable thing that can be applied to, again, both specific cases of mechanical and electronic systems. The same benefits exist here. But a bit more complexity makes it easier for that person who practices with this to transfer this knowledge to the real world task. And you know that real world troubleshooting tasks are much more complex that compared to what we saw in these two examples. Like you have to have a knowledge of the working of the system, specific connections, different components. There are sometimes more than 50, 60 types of different components that you have to know about and all the details. Do you have any question about this more complicated version of low fidelity troubleshooting? Yes. Yes, it is still low fidelity. It is still very abstract. It is just one step higher than the previous one, which was the most abstract material that you can find for training troubleshooting. But it is still, yes, considered as basic, low fidelity, generalizable type of training troubleshooting.
Now, since these two are fidelity simulators, like what actually bridges the gap between being a low than a high? Is it because like using technology like being a PC or something?
So once it becomes, what's the material, training materials, use knowledge of a specific system. Like there's like names of certain components. There's like, we'll talk about it in the next example. But once you see that it becomes like a specific system, like heating system or automobile engine or anything like that, once you get to that specificity, then you say that it's no longer low fidelity, at least in the realm of troubleshooting. But there is no like a sharp line. Some people would say low fidelity, and there are some materials that are mid fidelity, and then it becomes high fidelity. And it depends on the types of system and everything. But at least we can say that these two examples that we saw, because they are very generalizable, cannot be mapped to any specific system, but is shared in all troubleshooting tasks. They're both low fidelity materials. Any other question? So we'll see another example now, and it is the third type of system that the same line of research used. And so we saw two low fidelity simulators, but this one is kind of medium fidelity. And you see its difference by recognizing that it's no longer low fidelity. It's kind of a specific. And so it comes that the skills that people learn or trainees learn by practicing with that is no longer generalizable and abstract. And that system is something like this, that you see that components have names, still components and connections, but components have numbers, have names, and this is, for example, a mechanical system. And you should know the working of these components to some extent, or have some familiarity with the cost associated with replacing certain components, for example. And so this is like the internal working of that system. And there's also a kind of control panel that you see the status of the system and you take certain steps. That, for example, this system is this. The symptom is that, for example, the light will not turn on or something like that. And then you have the current status of the system. And here you have the actions of what actions you should take. And for each action, there is like an associated cost. So you see that it's a bit more like a real world system. And you have to use this specific knowledge of a realistic troubleshooting test. And it's no longer abstract, it's no longer node and connection. It's not just logical inference, but there are also other factors involved. So trainees at first are presented with the working of the system. And you saw that there are various types of components, not one, two, but many. And you see basically the control panel is showing the status of the system and the costs and everything. So first, trainees are presented with the status of the system, and then they see the control panel. And they can gather information by testing, again, connections to see which connections are working properly. So in these aspects, it's a bit similar to those low fidelity simulators. And they can do actions like removing components, and doing tests on those components, whether this component is faulty or not. And also, as we just saw, there is a cost associated with each action. And when the cost comes into equation, then the performance is no longer based on the number of steps. It is both number of steps and the total cost. And probably the cost is the most important aspect of performance here, just like real world troubleshooting tasks. So you have a system with faulty components, and you have one person or troubleshooter who finds the faulty component with lower cost than another person. That has a better performance. It's like taking your car to a mechanic and comparing two mechanics. One of them is fixing your car with cheaper price than another one, assuming that both of their troubleshooting has the same quality. And so you see that there are some basic similarities, but they're radically different. That's why this is no longer considered as medium, no longer considered as low fidelity. but it can be considered as medium fidelity in their categorization. And so you see this system, and here are the actions, for example. The connection between 4 and 5, like 4 and 5, this one, it's working because it costs $1, but it's normal. Connection between 26 and 30. Sorry, 26 and 30, this one. It says abnormal, which is not right. So there is something wrong in that area. 14 and 20. 14 and 20. This one. So 26 and 30 is saying abnormal, which was this. It's going back in this line, basically. That's why it's trying 14 and 20. It says not available or not. My guess is that it means that it's like having a 0 output or is not working properly, because in the next step it reaches 14 as abnormal, which is this. So when this is not available or is not working, then this tachometer generator is the faulty component, which is what they recognize here. And then you see that there is cost associated with testing each of these, but then it says, okay, this is not the 14 component number 14 should be replaced, and to replace it costs $199, for example. So you should have the knowledge of all of these, like the cost of components or something like that, in a separate sheet to be able to troubleshoot a system with the least amount of cost. So you see that here it makes more sense, because testing components is costly. You have to send someone, for example, in mechanical systems, to go and test, read the gauge or something like that, or even if they're like computer systems, those computer systems should have sensors. Those sensors should be maintained. So all of these are costly. And you see that there are certain costs associated with each checking, each replacement, each action. So just as the last question, what do you think are the benefits to this compared to the two low fidelity systems? Yes?
Even though it's probably going to be categorized as a fidelity simulation, still it seems like it would be extremely cost efficient. It's still pen and paper. If anything, it's just there's just more work put into trying.
Yes, it is still not considered as high fidelity, because if you just search in the internet, Google higher fidelity or current systems, troubleshooting systems to train troubleshooting of especially mechanical systems, it shows sophisticated systems that use things like VR or more sophisticated computer simulators, which are much more costly than what we saw here. You can still have this in a piece of paper. It's a bit more complicated, but still is possible to have it in that format. Yes, any other benefit? Yeah. Yeah, so because just like what we saw in identical elements theory, there are a lot of identical elements between this, much more identical elements between this and a real world system compared to the two low fidelity systems. It is more easily applied to that real system. And so higher fidelity, faster to apply to real world system is one benefit. And another benefit is still easy to deliver and distribute. Not as easy as those two low fidelity systems, but still easy. But the problem is that it has its own problems. And because we are short of time, I'm not going to ask you what are the problems, but the problems that it has is that it requires the learning about that specific system. So learning about it and doing that is much slower than those low fidelity systems because you have to spend time learning about the specific aspects of those systems, and is not as easy as those two low fidelity systems to deliver and distribute. This specific example that we saw was tested on a computer. It can be printed on a paper, but even if it's printed on a paper, you should spend a long time figuring out how it works and all those details. So, and the last thing is, of course, just what we said, it's not generalized. It's just a specific to a system. You learn of a specific system, and then another system, you have to spend another long time learning about another system. So the factor of generalizability is reduced.